Hi guys, welcome to another Learning Electronics Repair video. In this one we're going to look at transistors, in particular bipolar transistors. So all those who are going to comment that I didn't talk about MOSFETs and junction FETs and all sorts of other things, that's because I want to talk about bipolar transistors today. So here we have it, all you need to know about bipolar transistors to fix stuff. So what's a transistor? Well, it's a semiconductor device. They come in all shapes and sizes and a few variants, but basically they all have 3 pins on them, apart from the ones that have 4. So they really all have 3 pins on them, 3 legs. And the symbol for a transistor is this. And this is an NPN transistor. There's another type of transistor, if you like, which is the mirror image or opposite of this one. It's the PNP transistor. So a PNP transistor has a very similar symbol, but the arrow points the opposite way. Okay. And these two, if you like, are complementary to each other. They work in opposite ways. So all the voltage and polarities and the current flows on this are mirrored on this one. NPN, PNP. The 3 legs are called base, or B, commonly abbreviated to, collector, or C, and emitter, or E. So on this one we'll put as the number are B, C, E. That's how you'll see them. You also, when you find transistors on circuit boards and the actual circuit board has component markings printed on them, commonly these days a transistor will be marked as Q. So you'll have Q followed by number Q1, Q10, Q345. So this is just the reference number for the component, not the value of the component, not the type. On older circuit boards, you might find them quite often marked as TR1, TR7, and so on. But certainly in more recent stuff, and probably for the last 30 years to be quite honest, they tend to be marked this way. So that's one way to identify a transistor. I'll show you some physically in a moment, but unfortunately there are lots of devices that look like transistors but are not necessarily are transistors. So it can be a bit difficult sometimes to look at a PCB to know what the device is without testing it. Let's have a look at a few transistors to see what they look like, and then let's test a few, and we'll test them out of circuit initially. So we're going to do this using a semiconductor analyzer because they are cheap to buy these days and they're very handy and very useful. But we'll test them with a multimeter as well. So we're going to have a quick look at how we identify a PNP transistor, how we identify an NPN transistor, and how we identify which pin is which, and how we identify whether it is actually a good component or not. When you test a transistor with a multimeter, it basically looks like 2 diodes, and I'll just show you this now. So an NPN transistor to your multimeter looks like 2 diodes connected like this. Like so. So if we put the positive lead of our meter on the base, we will actually see effectively 2 diodes. And with a PNP transistor it's the same, but basically just the opposite way around. So with a PNP transistor it looks like 2 diodes like this. Okay, and this is your collector, this is your emitter, and this is your base. Now, just because a transistor looks like 2 diodes doesn't mean that you can make a transistor out of two diodes. You cannot actually make a transistor that way. But this is electrically how it looks to your meter. Now we know this, let's have a look at least a couple of transistors and see what we can see. Here is the test meter and here's a transistor. This is a TIP41C. I can't remember if it's PNP or NPN. So let's see if we can identify which type it is and which pin is which. So we'll go from one of the pins and I'll put the positive lead on it and we'll go to either of the other two. So here we see we get a reading 0.643. That is the junction, the semiconductor junction, the voltage dropped across it. And because we see a junction, we know one of these two leads must be the base. So let's see which one it is. Is it the middle one? Well, if we move the red to the other end, we should see the same or similar, and we don't. So this is not the base. This one must be the base, or it's a faulty transistor. So we go to the other end, and again we read 0.645. 643, 645. You notice these slightly different readings. Between the other two legs, we read nothing, okay? The open circuit. And if we go the opposite way round, so the black is on the base, we know this is the base, we get nothing. So the only time we ever see a reading is with the positive to the base. Okay? Because the positive is on the base, this is NPN. Think NPN. The base is always the different one, so P, okay? That's an NPN transistor. The other thing we can work out is that this reading is a little bit lower than this one. The one with a higher reading is the base emitter junction. So I'll just make a note of this rather than you just trying to remember it all in one go. This is our transistor, and we know, because we worked it out, base collector emitter. Now, with the positive on the base, what we should see is the diode junction going to the two other legs. So with the positive, the red lead on the base, to the collector, we read in about 0.6, yeah? And to the emitter, we read in about 0.6. 0.6, 0.6. Okay, to there and to there. Everything else reads open circuit. That's the only time you will see a reading. That's how you know where the base is. It's the one that goes to the two. And because it's the red lead, it is N, P, N. Okay? Because it's the red lead on the base. The second thing, as just pointed out, between the base and the two others that I get a reading, the one to the emitter is the one with the highest. 643, 645. So we know this is the emitter. Now we can test this in a moment with our component analyzer just to be certain. Let's test another power transistor. This is a big one. So let's stick it here and let's actually draw this again and let's mark the readings as we go along so you can see how to actually do this. Okay, so there's your three legs. Okay. There's the transistor. Because this one had the base on this leg, this might well be the same layout. So that's probably what you should try first. Is it the same layout? Okay. So let's have a look and let's see if it's NPN. So we'll put the red on here, which we think might be the base. Yes, we get a reading. So again, we know one of these two is the base. To this end, yes, we get a reading again. So we know it's like that one. And this is the slightly higher reading, okay? Everything else, any other polarity opposite way round between any of the other pins will read nothing. That's a good transistor. And we know, once again, base, collector, emitter, and this was the slightly highest reading, so that's the emitter. I've got one more similar shape to this. Let's have a look at it. It's a small one, but it's a similar sort of thing. So again, let's draw it, and then let's see if we can work out which one is which again. So again, we have three legs. Okay, let's go. We'll try it again the same way. Let's do it the same way. Positive to the base. Yes. Okay. But to there's nothing. 2.4. Okay. Ah, now this is reading differently. From here, I get a reading to here. Okay. You see it? And here I get a reading to here. This has a rather unusual reading. 808, 595, 595. It looks like, with the black in the middle, this is reading 558 and this is reading 593, which kind of suggests that that is the base in the middle and it is a PNP. That reads nothing. That reads nothing. So in that respect, you see it? Nothing to either end, black in the middle. (593), 559. So in that respect, this looks like base, collector, emitter, with a negative to the base makes a conductor. This looks like it's a PNP transistor, okay? That's how it looks to me. But this one, if we go between the other two legs, base collector, we're getting some readings, see it? Which suggests either this is a faulty transistor or there's something unusual about it. So we'll put that in the component analyzer. We'd have to put a question mark against it. It looks like a PNP transistor and the base in the middle, but it's a little bit odd. Let's look at two more and then we'll get our component analyzer and we can double check. So here is a small signal transistor. I don't know which pin is which. I can draw it. So we have a flat bit at the bottom. I'm doing it from underneath. We have 3 legs coming out. Okay, that's what we have. I don't know if you can see it's flat in the middle. I'll zoom down a little bit, you can see it properly. There we go. So once again, we need to find the base. So we're looking for one pin that conducts to the other two. So let's start with this end one. We don't know where it is. Let's start with the end. Let's go to the middle. That doesn't conduct with the positive on the end. Does it go to there? Yes. Go onto it again. Dropped it. Check the meter's working. Okay. Oh, well, I got a bleep and then it didn't. I don't know why it bleeped. Okay, so positive to this end doesn't seem to do anything. Let's try it with the positive to the other end. So let's turn this over. Let's go with the positive to this end. And again, we're looking for something that conducts. No. No. So positive to either end doesn't seem to do anything. Let's go with the positive in the middle. Let's try it again. Yes, that conducts. Okay. And that conducts as well. So it looks like the base is in the middle and it's red lead, so it's positive. So it's NPN. Always think the base is in the middle, and whichever letter is in the middle, NPN, it's an NPN. If it's a black lead, it's a negative, always the base in the middle, PNP. So we have 678, 677. So it's looking like I have to turn it round to match the orientation of this. It's looking like this is the base, and the one that was slightly higher is the emitter, which I think is, just dropped it again. Where's the emitter? The one with the slightly higher reading. 676, 678. So put it around the way it matches. Yeah, this is the emitter, and this is the collector, and it's with a positive here, the positive lead. So it's NPN. Okay, that's the transistor. If that's the case, then from either end shouldn't read anything either direction because it's collector to emitter. It doesn't read anything. Okay, and with a negative to the middle, to the base, it shouldn't read anything either way. Look, I've made this short. Try, yeah, nothing. Nothing. Okay, so we know that one is NPN. Last one. Moved a little bit. Another one looks the same. we'll try and draw the thing the same way up. So it's this way up. So again, it has the flat edge. It has round. It has 3 legs coming out. Okay. Let's see if it's the same. So we know the base was in the middle. And the positive lead went to the middle. So positive lead to the middle. So I've lost the meter. There you go. Positive lead to the middle. What happens? Nothing. Nothing. So either the base isn't in the middle or it's the opposite polarity. It's a PNP. Let's put the black lead in the middle. What have we got now? Yes. We've got a junction there. So one of these 2 pins is the base. Okay? It's reading 696. Is it the middle one, the base? Is it PNP? Yes, 697. So this one is the same layout. Base, emitter, collector. But it only conducts with the black lead in the middle, N. Always think black negative, red positive, yeah? So this is PNP. So there you go. That's how you measure them with a multimeter. Very commonly, these type of transistors will have the base on the left-hand side. Very commonly. Obviously, not always, because this seems to have it in the middle. These type of transistors, to be quite honest, it could be anywhere. There's no really set layout. I think every possible combination has been made by some maker or other. But let's now look at the component analyzer and let's see if we were correct in identifying all of these transistors. They all appear to be good transistors. We know if they're NPN or PNP. And we think we know the layout, collector, base, emitter. Let's see if we were right. And let's see what this thing is. Yeah. Now let's look at these transistors with our component analyzer. I have 2 here. So this is the very cheap one I got from AliExpress. It was about €6 or €7. And this is a Peak Atlas DCA 55. I've had this about 6 years or 7 or 8 years even. And this is my tool of choice. I picked this one up. Probably because I'm just so used to using it and I find it very easy to use. But this is like 50, 60 euros and this is about 6, so it's maybe 8 or 10 times the price. And I don't actually think it really gives you any advantage. But let's use them both and then we can have a look. So we'll do them in the order we checked them. So this was the first one. And we thought this was an NPN when the base was positive. Yeah, I didn't write it on. We thought this was NPN and we thought this was NPN. And NPN, PNP. That's what we think we've got. Okay, so let's have a look at the first one and we'll see. So we just put the leads on in any order. It doesn't matter which order we put the leads on here. Just put them on and then we can press the analyze button and let's see what it thinks of it. So test. NPN silicon transistor. It gives a bit of information. So the green is the base and the red is the emitter, and you can see it matches the layout that we worked out with the multimeter based on the emitter has a slightly higher voltage. Sometimes, occasionally, you'll find a transistor that doesn't work and the base collector, base emitter are the same. And there was only 0.01 difference on this, but there was enough to tell us, okay. So that's the actual transistor. This will also give us the gain. I'll talk about this in a little bit, HFE. And it just tells you the test current is 2.5 milliamps. And it's telling us the voltage base emitter is 0.68. That's the voltage at which the transistor turns on. Again, we'll talk about that in a moment. Test current of 4.73. Okay. Leakage current. Leakage is basically if the transistor is passing current when it shouldn't. So it's a good thing to use an analyzer. Now let's use the other one as well. And it'll probably give different readings, but I'm expecting it'll tell us the same thing. So it's testing it. Again, it's an NPN transistor. It's giving us a gain. And does it give us any more? No, that's what it gives us. But that's good enough. Base collector emitter again. So that confirms what we just read with the other one. So that's good, and the multimeter gave us the correct. Let's get this big one. These big transistors tend to have lower gain, by the way, I will say, than the smaller ones. Let's have a look. But obviously they can pass higher currents. That's the thing. And sometimes withstand higher voltages as well. But it's normally the current or the wattage that specifies the size. Okay, let's run test. Another NPN silicon transistor. Is the blue one the emitter? Yeah, blue one the emitter. So again, it told us it's an NPN. Note the gain is lower. That's common for a power transistor like this. That's the base emitter voltage, as I say, we'll talk about. And that's it. So we know it's another NPN transistor. We can do this with the little component tester. This is where it's a bit inconvenient because you can't get the thing in there, yeah? You'd have to, in fact, kind of like tag some wires on, so I'm actually not going to bother, but you could do it, yeah? You could do it. It's just not so convenient to do it. Maybe if we bend these two pins in, we might just be able to do it. Let's have a go. Let's see if we can actually hold it in place enough to get a reading. No, it's just in a dial. Let me try again. Yeah, it probably isn't making a contact. That's the top and bottom of it. Yeah. I don't think there's anything wrong. I'm just not getting a good contact against the transistor. But we know it's a good one. So have a look at this rather odd looking device that we found. Let's see what this thinks of it. So again, we think the base is in the middle on this one. So we'll put the blue on the base this time. Doesn't matter which one. We think the base is in the middle. We think the emitter is on the right hand side, but we're getting some strange readings between collector and emitter. What's it say? It's a Darlington transistor. Okay, that's why we have some strange readings, and I'll explain what one of these is in a moment. It'll have a very high gain normally. We got the blue as the collector. No, we completely read this wrong on a multimeter. Okay, the red is actually the base. So the multimeter would not read this. Diode protection between collector and emitter. Resistor shunt between base emitter. Gain not accurate due to base emitter resistance. 16. So that is not actually a bipolar transistor, hence the strange readings we got. But it's under the remit of this video, so we'll talk about it. This one. We think the emitter is on this end, so we'll put the blue wheel on the emitter. And by the way, I'll just come back to that other one, just check it in a moment on the other components analyzer, see what it thinks. Okay. So we've got the green on the base, we've got the blue on the emitter that we think is the emitter, and we think it's an NPN transistor. Battery. I have to get some batteries for this. I don't think I've ever changed the battery in this since I bought it. NPN transistor, that was correct. It goes this way up on our diagram with the flat side. So red is the emitter, which is correct. Gain 245. I can't remember why HFE stands for gain. Somebody will tell me. Or I can go and Google it. Turn on voltage, base emitter 0.72. Okay, that's that one. So we identified that correctly on our multimeter. Let's have a look on the little analyzer now. And let's have a look at this Darlington transistor as well. So here we go. Transistor in. What's it think? You see, this can't recognise it. It doesn't recognise it. It just says it's an NPN transistor. Yeah, with a forward voltage as that of 1.1 volts. This tester does not recognise this. We can check this part in a moment, and let's see if it actually is a Darlington transistor. Yeah, I have a part number. Right. Let's go to this one. So, emitter should be in pin 1, base in pin 2. Okay, so emitter should be pin 1, oh, pin 3, sorry. Let me look at the right way around. Just check. Yes, emitter's this end. So emitter in pin 3, my mistake. Again, not making a good contact. You see why I prefer the other one? Yeah, emitter in pin 3. Base pin 2 in the middle. So we got that right, NPN. Last one. Let's do it in this one first as we have it. So again, with a flat end, this way round, emitter should go into pin 3. See? Yeah, emitter on pin 3, yeah. Oh yes, forward voltage that thing is. Let's go one more time with this. We know this will find this, so I'll put it the same way as I had it. So the blue is on the emitter, green on the base, red on the collector. Okay. Yes, PMP, which is what we thought it was, and green is the base. Okay, blue is the emitter. So once again, the multimeter identified all the pins for us. So really, the only strange thing that came from that really is this one, which is a Darlington transistor, which basically is two transistors in one package, by the way. And I'm just going to check that because this component analyzer doesn't seem able to determine what it is. Here is the data sheet for that strange device. It was this one, MJE700. That's the actual device, the transistor. It's in that type of case. And if you have a look at this, it basically shows you what's inside this. So effectively, it has two transistors internally connected, whereby the emitter of one goes to the base of the other one. And the idea of this is it basically increases the gain. So the total gain, the current gain, is the gain of this transistor multiplied by the gain of this transistor. You will see it has an internal diode and it has two internal resistors from base to emitter. And this is what the peak analyzer was telling me and saying it couldn't give me an accurate gain figure because of these resistors and that it had an internal diode. Whereas the El Cheapo component tester just could not recognize this. So there's another good reason why I actually prefer to use the peak analyzer. So there we have a few examples, and you can see that the multimeter could identify all of them apart from this. It gave us completely wrong pinout, and it had some strange readings. The El Cheapo could identify all of them apart from this. So in a lot of ways, it was no better than the multimeter was. Yeah. This one could identify all 5. Let's just have a quick look at a few transistors. So transistors come in all sorts of shapes and sizes. These are some older ones. They're like little tin cans, little top hats, basically. On older equipment you will find those. There's more of them here, sometimes like this, but a much larger tin can, basically. You'll also find, I mean, these are more the plastic ones, but they're bigger. So really these transistors will come in all sorts of shapes and sizes. Little plastic ones again, like that sort of shape, yeah. And we have just show you these are old power transistors, package called T03 or T03, probably obsolete for any current devices, but you'll find these especially in old amplifiers. It is another one similar to these. If you find transistors with a metal tab here on the back, almost always you'll find that metal tab is actually connected to the collector, which is the middle pin. We can just check this. We'll put the meter on here and we can just go to continuity range and we can have a look. So this metal tab is connected to the middle pin, okay, on all of those. Has this one got one as well? This Darlington, is it connected to any of them? It goes to the middle pin again. Yeah, it goes to the middle tab. This means normally when you find one of these mounted on a heatsink, which is what they're designed to do, that either the heatsink will be at the same voltage as the collector of the transistor in the middle tab, or there will be a mica washer or a plasticky, rubbery type grey washer between here and the heatsink. And if they're this type, not only will there be a washer and heatsink compound usually, there'll also be a plastic insert in here so the bolt going through doesn't contact the metal. It's very important when you're repairing stuff to watch out for that and put the insulators back in when you replace the transistor. Otherwise you'll short it to the heatsink and you'll just blow something up again most likely. I'll just show you one more. You're unlikely to find these. These are vintage components really, but this is a photo transistor. So effectively by shining light on it you can change the gain of the transistor or make it effectively pass more current or less current by the intensity of light. So that's a photo transistor. I'll just mention now, seeing this as everything you need to know about transistors to fix stuff. These transistors we've been discussing are silicon transistors. And they have, as you can see with the test meter when we're measuring, these voltage drops across the semiconductor junctions of about 0.6 of a volt, roughly speaking. If you're working on vintage equipment, you may also find germanium transistors. These were used certainly in the 60s, 70s, and these transistors have a voltage drop of about 0.2 volts across the semiconductor junctions, base to emitter, base collector. You'll only come across them in old equipment, I would say. I'm trying to think of any specialist uses for germanium transistors these days. I don't know, but I haven't studied that, so maybe somebody can correct me. But just be aware you may come across these on very old equipment. And to be quite honest, they tend to have some strange failure modes, which you don't see in modern transistors. And it's probably a topic to itself. So I'll leave it at that with that one. But if you are going to be working on old, very old amplifiers and transistor radios and these sort of things, then you do need to know about them. Let's have a look at how transistors work, and not from the physics of how they work, but an analogy of how they work. So an NPN transistor can be considered using the flow of water. So imagine we have a water pipe, a wide water pipe, a mains water pipe, and we have coming into it a smaller water pipe. And this water pipe is connected to a pump that can apply pressure to the water. Pump in there. In here we can imagine now that there's a valve. So the valve effectively is pivoted and sits here. And as you apply pressure, you open the valve, allowing water to flow through here. But until you apply a certain amount of pressure, no water will flow. It takes a certain amount of pressure to overcome the inertia, the mass of the valve before it will open. This valve is connected to another valve inside here, effectively, that can move in and out. Quite how it does it without the water leaking, we won't go into. But it's attached like this. So as you open this valve, it pulls this valve open, and this is the larger pipe. So basically, with a small amount of water flowing through here, by varying the pressure, you can control a larger flow of water flowing through here. And that's basically how your transistor works. This would be your base, the control terminal, the valve. This is your collector, and this is your emitter. This is for an NPN type transistor. Okay, so that's basically how it works. There's a few things that you should just consider here which are important. First of all, no water will flow through here until you reach at least a certain pressure here to start moving the valve. Okay, that's the first thing. The second one, the current, the water flow flowing through the collector to emitter is greater than from the base to the emitter. Okay, and the current that's flowing through the emitter is actually the sum of that and that, because this water, the small amount, is also coming through here. So flowing through here, you have both the flow of water coming from the base and the flow of water coming from the collector. Okay, that is basically how an NPN transistor works. I'll show this now electrically. So all we've got to really do now is consider pressure to be voltage and water flow to be current, electrical. And then we can consider how a transistor works. So we'll do the NPN first. This is probably the most common way of using a transistor. So we have the collector connected to a positive supply via a resistor, or this could be effectively a load, a light, a relay, a small motor. It's a load, okay. And this is your base. So basically we have to use resistors. This resistor, or the resistance of the load, sets the maximum current that can flow through the transistor. If you exceed the maximum current for that type of transistor, you'll burn the transistor out. It can only handle a certain amount of current. And the same with the base. You can only have a certain amount of base current as well. So normally you have a setup something like this, and this has a small positive supply. Okay, this is the big positive supply, this is your small. With the semiconductor junction, that's from the base to emitter, we've just measured with our test meter, and it measures about 0.6 of a volt. So basically you have to apply 0.6 of a volt here before anything can happen at all. So while the voltage here, and let's just do a little graph out, graphs, not very technical graphs. This is voltage, and this is current, amps. Okay, and this is on the base. This is the base, yeah. So the base voltage has to go from 0. Let's make it somewhere 0, 0.3, 0.6, 0.9. Yeah, this is your base voltage going up. Okay, until the base voltage reaches about 6, nothing will happen. Basically, no current will flow. At the point it reaches 6, the current goes up very rapidly. So by the time it's gone from 0.6 to 0.7, it's probably gone from not conducting at all to its maximum conductance. It's now switched on, and it cannot switch on anymore. This area here, before the transistor can switch on, before you get to 0.6 volts, this is called cut off. Okay, there's only one T in it. Cut off. The transistor is cut off, so it can't switch on. Once you get to this point here, it cannot switch on anymore. It's saturated, or a more common term, it's hard on. Some of you are gonna like that, aren't you? It's hard on. It's got a hard on, yeah. So that's basically how your transistor behaves. I hope you can see from this, a transistor is basically a current amplifier. It amplifies the current. So for a small control current flowing in through the base, you can control a large current from the collector to emitter. And that's basically how an NPN transistor works. Transistors are generally used in 2 ways, although the circuits they are used in can be very varied. The transistor itself is actually in 2 ways. It's either acting as a switch, so you either have no volts on the base, no current flowing, or you have enough voltage, 0.6, 0.7, for the transistor to be fully conducted. So it's either off or it's on, and it's nothing in between. That's one way it can be used, as a switch. The other way a transistor can be used is an amplifier. So with an amplifier circuit, basically you have usually 2 resistors to a base. This is very much like what I had before. Let's put a load on. Let's put a speaker, okay, a loudspeaker. This is your positive supply, okay. This is ground, and this is ground. And with this, you basically set, I mean, the supply could be 9 volts, 12 volts, 100 volts, whatever. But with these resistors, you set the transistor, the voltage at the base, to be halfway through this. This bit between 0.6 and 0.7 where it goes from being fully off to fully on. You can set it, for example, to be about halfway. So the transistor's half on and half off, okay? If you now maintain that DC voltage and you apply an AC signal through a capacitor, so you're not affecting the voltage. Capacitors pass AC, not DC. So you can now put a small signal on here, and it'll vary the voltage between about 0.6, 0.7, yeah, between this point and this point, and effectively for your small signal going in, you get a big signal coming out, roughly between whatever voltage the supply is and ground. Okay, so a signal here may be 0.1 of a volt, peak to peak in this circuit can give you a signal, the same signal, peak to peak, with 9 volts amplitude. The other thing you need to just realise about transistors, and this is whether they're a switch or whether they're an amplifier. I'll draw a circuit with some voltages and you'll see. Very simple. Base, emitter, resistor, collector. Okay, that's your transistor. Let's put plus 12 volts on it. Okay, and this is your base. Same as we did before. We'll use this as a switch, and we'll put a voltage on here. When there's no voltage on the base, so this is 0, the transistor is switched off. It's not there. Okay, so what voltage will there be on the collector if the transistor isn't there? Well, basically no current is flowing, so the voltage here will be the same voltage as the other end of the resistor, because no current flows through the resistor, so there's no voltage drop across the resistor. So when this is 0, the voltage here is 12 volts. Okay, now look what happens when we put some voltage on here. Let's put some voltage on here. We'll put enough voltage into this here so that the base of this goes to 0.7 volts. Okay, this is now passing current, and this is now passing a larger current. Okay, the current being set by the value of this resistor. What voltage on the collector now? Well, basically now this end of the resistor has 12 volts on, and this end of the resistor via the transistor is connected basically to ground. There'll be a small voltage drop across this. When it's switched fully on, this doesn't go to the voltage there, 0. It might have 0.1, 0.2 of a volt. So the voltage here will be about 0.1 of a volt, 0.2 of a volt. Okay, so look what's happening. When the voltage here is 0, the voltage here is 12. When the voltage goes up to 0.6, 0.7, the voltage here comes down to 0. When you switch it back to 0, this goes back up to 12. So it's switching. You're switching it, but you're inverting the polarity. Can you see that? When the transistor is turned on, this has a positive voltage on it. And when it's turned on from the collector, this is held down to ground. And the same applies with this amplifier. I'm sure you can see that now. So as this signal goes more positive, the transistor turns more on. In actual fact, what you see is that the waveform, this is getting more positive on the collector here. This is getting more negative. Okay, it's upside down. It's inverted. And as this goes through 0 to more negative, this goes to more positive, and so on. So a transistor is a switch, is an amplifier, and it also inverts the signal. I made a couple of videos, I think it's 2 or 3, I'll link them from here. So I made a series, Transistors for Beginners, where I went much more into the general use of transistors. But for this tutorial, remember, we just want to fix stuff. I think that's really all you need to know about NPN transistors. Now let's have a quick talk about PNP transistors, and something that confuses a lot of people. And to be honest, it confused me when I was beginning, and if it confused me, I'm sure it confused a lot of others. So let me tell you about the PNP transistor. Here's our NPN transistor. We'll use it as a switch, same as we were just doing. but it applies to an amplifier. Okay. And then we'll have a look at the PNP transistor. So here we have plus, positive. Okay. So we know, we've just looked at it. To switch this transistor on, you need to apply on here about 0.6 of a volt, positive with respect to the emitter. Okay. The base has to be a higher voltage than the emitter by about 0.6 to switch it on. With a PNP transistor, it's actually the other way around. So with a PNP transistor, we'll draw it like this. And we can in fact put a load here, although it doesn't have to be. Could be in this leg. And we'll have the same thing. Okay. Now with a PNP transistor, instead of the base having to be more positive than the emitter to turn the transistor on, with a PNP, the voltage on the base has to be more negative than the emitter. So you have to apply a voltage here of about minus 0.6 to turn this on. And when you turn this on, the voltage on the collector will basically go to the same voltage as the emitter. It's almost like a short. Okay. So you might think from this, a PNP transistor needs a negative voltage supply to work. Okay? Push the ground. That is not the case. A PNP transistor needs to be base to be more negative than the emitter. It doesn't have to be a negative voltage with respect to ground. So, for example, if this supply here again, positive, 12 volts, okay? To switch this transistor on, the base has to be, as I say, 0.6 negative of the emitter. So the voltage on the base has to be about 11.4 volts. Positive with respect to ground. Okay? So that's something you just need to get your head around. When I was at the beginning, it took me some time. I thought PNP transistors need negative batteries. They don't. Yeah, they don't. It's all relative to the emitter. I'll talk a little bit more about this when we look at how to test transistors in a circuit. Now let's have a look at what goes wrong with transistors. We want to fix stuff, yeah, so we've had enough of the complicated theory. What goes wrong with them? This is what we want to know, and how do we find the faults? Okay, so the main ways a transistor fails is to go short circuit. Okay, they go short. And they can go short between any or all of the terminals. So they can go short base to emitter, they can go short base to collector, and they can go short collector to emitter, and any combination of all three, collector, base, emitter. I think that's all the combinations. So they can go short between any of the terminals or all three of the terminals. The other way they fail is the opposite. They go open circuit. And again, they can go open circuit between any of the terminals or all of the terminals. So that's the main ways transistors fail. They can also fail in as much as they go low gain. I mentioned this. So a transistor that's low gain is, imagine it like this is opening and shutting, it's working, yeah, but there's some slack in this cable. No, not some slack. Better say, this cable is like rubbery. It expands, it will stretch, okay? As well as moving this, it can stretch. So at the right pressure, it starts to turn on, but because of the fact this can stretch, it's like elastic, this doesn't move as much as it should do. And even when this is fully open, this is not open enough. So effectively, the current flowing through here is less than it should be when this is fully conducting. It's low gain, okay? And while I've still got the diagram, we can just look at another failure which I'll tell you about, which is leaky. So with the one that's leaky, imagine the rubber seal on this thing has gone. So even when it's shut, a small amount of current still flows through here. Yeah, a bit like your toilet cistern, yeah. The valve's shut, but it's still trickling water into it. So those are two other common ways that transistors can fail. So we have low gain and we have leaky. Transistors can actually fail in quite a few esoteric ways. They can go noisy, they can become temperature sensitive, so the gain's varying too much as temperature changes. They can do some pretty weird things, to be quite honest. And the weird things they can do, I think you'll find them more commonly in analog circuits such as amplifiers, radio frequency circuits, and these sort of things. I'll be quite honest with you, that's something of a specialist subject on its own. So although this is all you need to know about transistors to fix stuff, I will say I need to do another video specifically for those type of circuits that discusses the problems where we have noisy transistors and problems with gain, and in amplifiers in particular, transistors where the gain isn't matching, so you have a number of transistors all in parallel effectively handling a load and the gain between the transistors doesn't match. Two other things I'll mention. Transistors can fail, especially in amplifier circuits again, where this I choose another page, yeah, this one. If there's a problem with these resistors, these are called bias resistors. So the idea of the bias is that it holds the transistor in its quiescent state, partially conducting, or just on the point where it will start conducting. And problems with these bias resistors can affect the way the transistor works if it's not biased properly. So that's something you need to just bear in mind. And the other one is that you often find transistors connected like this type of circuit. So again, we'll have a resistor, ground, and we'll have a resistor, and then this is connected to another transistor like so, and in various formats, yeah, this sort of thing. And maybe this is connected to something else. Maybe this is connected to a PNP transistor coming in this way from the 12 volts, yeah. So you can get this type of circuit, and with this type of circuit we can get a failure whereby if one of these goes short circuit, it will damage the next one, and that will damage the next one. So you get this cascade effect where one transistor failing will cause all the others to fail in the circuit. That's common again in audio equipment. Can we test transistors in circuit? Yes, we can, and there are two ways in which we can do it. This will not always allow you to find a faulty transistor, but we'll certainly find a short circuit one, and you may well find an open circuit one as well. So in those type of faults, then yes, we can test them in circuit. And to do this, we need to use the diode mode on our multimeter. So we're in diode mode, and let's have a look. There's a few old circuit boards here. This is off an old ATX, and there are two transistors down here. Now, if we try to test these in circuit, I'll just find where they are. I can see 3 pins here. We should be able to see the semiconductor junctions, but we may not always be able to. So let's have a look. Well, there's a semiconductor junction there, okay. And there's one there, so this is looking like it's the base. And these looking like the collector's normally in the middle on this type of transistor. But we can try the voltage method. 540, 564. That's the emitter, the higher voltage. What happens if we go the other way? Nothing, that's fine, there's nothing. We see a reading here, another diode junction. Now that is almost certainly due to another component around here that's causing that reading. And again, we see them between the collector emitter, but not that way. So you're tending to see more diode junctions than you would expect on a transistor. Let's have a look at the other one. Nothing there. So that's reading that way, like 0.610. If it's the same as that, this should be the base, we would imagine. Yeah. Emitter. So we're seeing that. Nothing that way. So you can see we can test them, but we're seeing more diode junctions than you would expect. Well, if you have a short, it will be obviously there's a short circuit there. So shorts you can find. When you get a situation like this, there are two ways really you can test the transistor. You can either take it out of the circuit board if you suspect it, or if you just want to test them. You can take the transistors out and just test them out of circuit. That will give you a very good indication. You'll also be able to see the gain as well. So you'll be able to, for example, in some circuits, amplifiers, you may have to match the gain. So you'll get like 4 or 8 transistors driving the output, and they have to be matched for gain. So you can also do that with a transistor tester. Let's have a look at 1 or 2 more. So let's find some surface mount transistors. So SMD transistors look like this. Let me zoom down, you can see them a little bit better. These appear to be SMD transistors. This little package is called SOT23, which is small outline transistor, SOT. 2.3 is the size, 2 millimeters by 3 millimeters. And you find a number of other larger packages, especially for higher powered components. So these could be SMD transistors. But the problem is that there's lots of devices made in this package. They could be MOSFETs, which we'll do another complete tutorial on. They could just be diodes, either a single or a double diode in the package. They could be a bipolar transistor. The best indication that they're going to be transistors of some sort is that the part number is Q. Not the part number, but the identification number. Q662, Q661. Yeah. So let's have a look at these and see if we can see any semiconductor junctions. Normally with these, the pin that's on its own is the collector. And usually this is the base and this is the emitter. But I'd say usually. I mean, these looks like these 2 pins are actually connected to each other, which is not uncommon to find. So let's have a look. Let's see if we can see any junctions. So we'll go from here, and we'll go to here. Well, that means open. So if this is the base, it's not an NPN transistor. Here. That just gives a reading, but it's not a diode junction. It's not a semiconductor junction. Does this one give? Yeah. We can't see any semiconductor junctions there. What about between this pin and this one? No. No. Now let's try it with the negative on this end. We haven't tried this yet. So we'll put the negative to here. No. No. So we get a little bit of a reading even there, but we're not seeing any junctions. So you can see straight away that we have a situation where that either A, these are not bipolar transistors, or B, that they're faulty. The only way to find out what they are is they have a code on here. This is not a part number, it's an SMD code. The easiest way to find, if you are going to find them, is obviously use Google. And if you search for SMD code and then the size of the package, SOT-23. Yeah? If you search for that, you'll probably find what they are. And it might be only the first couple numbers in this SMD code, actually, the part number. The other two is possibly a date code. But via that method, so SMD code SOT-23 or SOT space 23, yeah? And that will probably find you the part number. Now, once you get the part number from the code, you can then look up the data sheet and figure out what that actually is. The other possibility is just to take it off the board. They're quite easy to unsolder. You may have to tag some little wires on it and use a components analyzer and see what it is, yeah? So that's one. There's another one here. Let's see, is this a transistor? We don't know. Again, this is on a thick track, so it's probably the emitter. This is probably the base, but it could be a MOSFET again. So let's have a look what we've got. Nothing there, nothing there. Go the other way around. Yeah, a reading, but it's not a semiconductor junction. Okay, so again, we can't read anything from that, and we'd have to look up the code again. SMD code. Yeah, SOT-23, and now we'll see if we can find out what that is. So you can test transistors in circuit. I've shown you 2 examples, but it'll probably only reliably find short circuit transistors for you. We can see that testing transistors in circuits can be problematic. you can normally spot a short circuit transistor or short circuit junction. Occasionally in circuit, even that will let you down. So you can sometimes get circuits similar to I've shown you, where you have resistors on the base. I'll draw an NPN transistor again. This type of circuit. And this resistor can be a low value. It can be sometimes a very low value. And in this type of circuit, if you measure across the base emitter, you'll probably see a short or near to short. And in fact, it's the base resistor that you're seeing. The only way to find that out is to take the transistor out. So if you take the transistor out and it's actually okay, look, see if some low value resistor. And occasionally you'll find a similar circuit, but there's a coil here, an inductor coil, maybe even a transformer, this sort of thing. And again, this coil can read practically short to your multimeter. So sometimes that will let you down. Are there any other ways of testing transistors in a circuit? Well, yes, actually there is, and this is actually probably more reliable. So this, assuming there's no shorts, we'll look for shorts first, is to actually use the voltmeter to test the transistors. And there's a few simple rules. If you follow these rules, it will get you a long way. So one of them is that between the base and the emitter, you can't have more than 0.6 of a volt. Okay, if you've got a circuit, these resistors are getting very dodgy. There we go. Something like this, okay. And we'll put a load in here, put a speaker. Okay. So if you measure more than 0.6 of a volt, say 0.7 of a volt between the base and the emitter, you can say with a very good degree of certainty that the base emitter junction is open circuit. Now, when I say measure more than 0.6, I don't mean that if you find a transistor with more than 0.6 volts on the base, it's faulty. Because you can have a circuit commonly like this one, put some resistors in, we put our transistor in, and we have a resistor going into ground, and we have either, well, in fact, we can actually go like this, okay, this sort of circuit, or again, we can put some sort of load in here. In this sort of circuit, if you measure from ground, so you put your black lead on here, and you put your red lead on here of your meter, you'll take your multimeter and you measure it. Okay, you might find like 4 volts or something here. It doesn't mean that this junction is open circuit, it just means that the emitter isn't ground. So the most reliable way to test a transistor is this. First test, and let's use a different coloured pen. Is there a short between any of the terminals on the transistor, base, emitter, collector? If there isn't a short, measure from the emitter, not from ground, from the emitter to the base, and put your probes here on your test meter. Okay? So you're measuring directly base to emitter. Do you see more than 0.6 volts? If yes, so if it's greater than 0.6, let's say 0.7, I mean quite a bit greater, 1 volt or more, yeah? If it's more than that, you got base emitter as open circuit. You got a faulty transistor. Okay, this is for NPN, we'll do PNP in a minute. Right, third one. If the base emitter is near to 0, certainly less than 0.6, yeah? If there's less, direct between the base and the emitter with the emitter probes, positive to base, then the transistor is off, okay? So if we measure from here, emitter to collector, directly across the transistor, okay? Put your multimeter here. Now, if the transistor's off, less than 0.6 on the base, then we should read a voltage across here. And the voltage probably is a voltage between ground and the power rail, because no current is flowing. So it's effectively the same as measuring here and here. So the transistor is off, then you'd expect between collector and emitter to be a voltage. It's off, yeah? Number 4, base emitter is about 0.6 volts. Okay? The transistor's on, 0.6 positive. Now, if we measure between the emitter and collector, this transistor should be turned on. So the voltage across here should be almost zero, maybe 0.1 or 0.2. Okay, so the transistor is on, and collector emitter equals about 0.1 volt, 0.2 volt, something like that. So that's how to test a transistor by measuring voltages. You can measure from ground, guys. You can put your black lead on here. You can measure the voltage on the emitter, and then you can measure the voltage from ground to emitter, ground to base. Subtract this voltage from this one. So if this is reading 3 and this is reading 2.4, you know it's switched on. But it's easier to do it this way. Okay. Again, you can measure from ground to emitter, or ground to collector, and depending on the difference, you can work out if the transistor is conducting or not. But I would suggest, at least if you're beginning, do it that way and you won't go far wrong. Okay, PNP transistors. The same as applies, but with PNP. In number 2, yeah. So base to emitter. This is again with your red lead on the base, yeah. Always put your red lead on the base, okay. Base to emitter. Now, if it's more than minus 0.6, yeah, -1, -2, -3, base emitter is open. The same as 2 there, it's just minus, yeah. The same with this one. I don't really need to write it out again, but number 3, if base to emitter, yeah, I will write it out again. If it's about 0, or it's certainly less than minus 0.6, the transistor is off. And between the collector and emitter, you expect to find the voltage. Because it's PNP, you'd expect to find the collector is actually going to be lower than the emitter rather than higher. And then the last one, the same. If base emitter is about minus 0.6, then the transistor is on, and between the collector and emitter should be very low voltage. Again, the collector should be slightly lower than the emitter because it's PNP. So if you look at those basic rules, you can test most transistors in circuit. So there we have it. All you need to know about transistors to fix stuff, mostly. Amplifier circuits, particularly audio amplifiers, RF amplifiers, are kind of an art within themselves. There's a number of topics specifically to that type of circuit that are really outside the scope of this video. But don't you worry, I will do at some point a video, all you need to know about amplifiers to fix stuff. So for now, I think I've given you a lot to go at. You can see, if you make a note of this, the best way to test a transistor in circuit is with the device powered up and by measuring voltages, other than the fact you can find shorts. Okay guys, hope you enjoyed that short video, and I'll see you all soon on another Learn Electronics Repair video. Ciao for now guys.